Hello lovely students, welcome to this section on inverse of relations and their graphs. Inverse of a relation is a relation formed by interchanging ordered components of each of the ordered pairs in the given relation. If the given relation is presented in the form of an ordered pair x, y, then the inverse of that relation will be determined by interchanging or swapping the ordered components of x and y, and it gives us an ordered pair y, x. As an example, let's see this relation. If R equal to a relation containing these 6 ordered pairs, then find the domain and range of the relation. Find the inverse of relation and its domain and range. Domain of relation equal to, domain is a set containing values of x in the given order pairs. In the given relation, the values of x are 0.5, 1, negative 4, a, 10 and negative 2. Let's list out these values in the brass starting from letter A and arranging the numbers in increasing order. Among the numbers, the smallest one is negative 4, then negative 2, next is 0.5, and then 1, and the biggest number is 10. Range of relation equal to, range is a set containing y values. Y values here are 6, 0.25, 3, negative 3, b and 7. Again, let's list out these values starting from letter B and arranging the numbers in ascending orders. Negative 3 is the smallest among these y values, then 0.25, then 3, then 6, and the biggest is 7. The other query is find the inverse of the given relation. The inverse of relation, which is designated as r the power of negative 1, is equal to, as we discussed above, for a relation given in the form of order pair x, y, its inverse is determined by interchanging the ordered components of x and y. The first order pair is 0.5, 6. Interchanging these two gives us 6, 0.5. The second order pair is 1, 0.25. Swapping 1 and 0.25 gives us 0.25, 1. The third order pair is negative 4, 3. Interchanging them gives us 3, negative 4. Applying the same rule, the rest 3 order pairs become negative 3, a, b, 10, and 7, negative 2. Domain of this inverse relation equal to, letter B. Among numbers, the smallest is negative 3, then 0.25, then 3, then 6, and the biggest is 7. Range of inverse relation equal to, letter A. Negative 4 is the smallest among these y values, then negative 2, then 0.5, and then 1, and the biggest is 10. Comparing the domain and range of the given relation and its inverse, we witness the following two realities. The first reality, domain of the given relation is always equal to range of the inverse relation. As we can see here, the elements of both these sets are a, negative 4, negative 2, 0.5, 1 and 10. Second reality, range of the given relation equal to domain of inverse relation. In this particular case, range of the given relation and domain of the inverse relation contain the elements b, negative 3, 0.25, 3, 6, and 7. By the way, these two realities or these two general formulas hold true for any relation and its inverse. As we discussed in part 1 of this installment, relations are not only expressed in the form of a set of order pairs, rather, with different ways of expressing relations. The most common one is by using equation. If a relation is given as an equation using variables x and y, Then the inverse of that relation is obtained by replacing every x in the equation with y and every y in the equation with x. Let's see this equation as an example. Let R equal to unordered pair x comma y such that x and y are element of real number and 3y equal to 2x minus a. Find R inverse. The inverse of this relation can be expressed in two different ways. First, keeping the order pair x comma y as it is, but interchanging x and y in the equation. Second, swapping x and y in the order pair, but keeping the equation as it is. Let's see each of them step by step. R inverse equal to unordered pair x comma y such that x and y are element of real number and 3 times in place of y we have to write x equal to 2 times in place of x we have to substitute y minus a. In this equation x is written in terms of y, but it's common to express y in terms of x. We can rearrange this expression in order to write y in terms of x, meaning R inverse equal to order pair x comma y such that x comma y element of real number, and when we take minus a to the right of equality sign it becomes plus a. Dividing both sides of the equality by the coefficient of y gives us y equal to 3 over 2x plus a over 2. The second way of expressing the inverse relation is swapping x and y in the order pair and keeping the equation as it is. That's R inverse equal to unordered pair x comma y becomes y comma x such that x comma y element of R and 3y equal to 2x minus a. Bear in mind, we can't make both changes at a time. It's impossible to swap x and y in the order pair and in the equation at the same time. The inverse of the given relation can also be shown by drawing a graph. Draw the graph of the inverse relation R equal to unordered pair x comma y such that 2y greater than minus x plus 2 and negative y less than x plus 1. R inverse equal to unordered pair x comma y such that 2 times we have to substitute y by x greater than negative x becomes negative y plus 2, and the second inequality negative y has to be substituted by negative x less than x has to be replaced by y plus 1. Let's rewrite y in terms of x. This relation equal to unordered pair x comma y such that 2x, when we take plus 2 to the left of greater than sign, it becomes minus 2 greater than negative y, and negative x. Again, when we take plus 1 to the left of less than sign, it becomes minus 1 less than y, which is again equal to unordered pair x comma y such that 2x minus 2 greater than negative y means negative y less than 2x minus 2. To convert the coefficient of y from negative to positive, we have to multiply both sides of the inequality by negative 1. Negative 1 times y is y. When we multiply both sides of the inequality by negative 1, less than sign becomes greater than. Negative 1 times 2x is negative 2x. Negative 1 times negative 2 is plus 2. When we move to the second equation, negative x minus 1 less than y means y greater than negative x minus 1. Now, we found out the inverse of both inequalities, and hence we can cast forward to draw the graph of inequalities by following the steps. Step 1, draw x-axis and y-axis. X-axis is left-right arrow and y-axis is up-down arrow. The point where the two axes intersect is the origin, which is 0, 0. The arrow to the right of the origin is positive x-axis. To the left is negative x-axis. Upward the origin is positive y-axis, and down the origin is negative y-axis. Let's divide each of the axes to equal segments and mark points where the numbers fall. Step 2. Find any two order pairs for each of y equal to negative 2x plus 2 and y equal to negative x minus 1, preferably x-intercepts and y-intercepts. These two equations are generated simply by substituting these two greater than signs by equality sign. Intercepts are preferable because at the intercepts, either of the two variables is 0, hence we can solve for the other variable easily. At y-intercept, x equal to 0. Substituting 0 in place of x in the first equation gives us y equal to negative 2 times 0 plus 2. Negative 2 times 0 is 0. 0 plus 2 equal to 2. So 0, 2 is the y-intercept of this first equation. When y equal to 0, meaning at the x-intercept, 0 equal to negative 2x plus 2. Negative 2x plus 2 equal to 0 only when x equal to 1. Thus, x-intercept of this equation is 1, 0. When we move to the equation y equal to negative x minus 1, if x equal to 0, y equal to 0 minus 1, which is equal to negative 1. So the y-intercept of the second equation is 0, negative 1. If y equal to 0, 0 equal to negative x minus 1, this implies negative x minus 1 equal to 0 only when x equal to negative 1. Thus, negative 1, 0 is the x-intercept of the second equation. We can locate this intercept on the xy plane we drew. In an order pair 0, 2, x is 0 and y is 2. X is 0 on the y-axis and y is 2 at the second mark on the positive y-axis, meaning 0, 2 is 2 units above the origin. 1, 0 is this first mark, which is 1 unit to the right of the origin. 0, negative 1 is 1 unit below the origin, and negative 1, 0 is 1 unit to the left of the origin. Step 3. Draw a straight line that passes through each of these two order pairs or each of these intercepts. The choice of which type should be used depends on the nature of the inequality. If the sign of the inequality is less than or equal to or greater than or equal to, we will use solid lines. If the equality associated with the inequalities is missed, meaning if the sign is less than or greater than, we will use dashed line. By using solid line, we convey a message that an order pair on the line is part of the relation. Order pairs on dashed line are not part of the relation. In our relation, the inequalities are greater than. Thus, we have to use dashed lines to connect the two order pairs. The line that passes through 0, 2 and 1, 0 is this kind of downward sloping dashed line. The name of this line is y equal to negative 2x plus 2. The intercepts of y equal to negative x minus 1 are 0, negative 1 and negative 1, 0. The line that passes through them look like this. The name of this line is y equal to negative x minus 1. Step 4. Shape the region that satisfies both inequalities. These two dashed lines divide the graph into 4 different regions. We can arbitrarily assign names to these regions. We can say region to the left of the lines as region 1, the region below the lines as region 2, the region to the right of the lines as region 3, and the region above the lines as region 4. The order pairs that satisfy both inequalities lie on one of these 4 regions. To identify that region, we have to take one order pair from each region and check with the inequalities. Let's find the point of intersection of the two lines because it's important to pick an order pair in each region. The equation of the two lines are y equal to negative 2x plus 2 and y equal to negative x minus 1. We can subtract equation 2 from equation 1 to remove y from the equation and solve for x. That's y minus y is 0 equal to negative 2x minus negative x means negative 2x plus x, because negative times negative is positive. So negative 2x plus x gives us negative x. 2 minus negative 1 means 2 plus 1, which is equal to 3. Negative x plus 3 equal to 0 means x equal to 3. We can take either of the two equations and solve for y by substituting 3 in place of x. Let's take the second equation, that's y equal to minus x minus 1. Substituting 3 in place of x gives us y equal to negative 3 minus 1, which is equal to negative 4. Thus, the two lines intersect at 3, negative 4. 0, 0 is in the region designated as region 4. Let's check it with the two inequalities. The first inequality is y greater than negative 2x plus 2. Substituting 0 in each of x and y gives us 0 greater than negative 2 times 0 plus 2. This implies 0 greater than negative 2 times 0 is 0. 0 plus 2 is 2. 0 greater than 2 is false. By this calculation, we understand that the order pairs that satisfy both inequalities are not in this region. Let's check region 3. All order pairs to the right of 1, 0 are in this region. We can use 3, 0. Plugging 3 to x and 0 to y gives us 0 greater than negative 2 times 3 plus 2. This implies 0 greater than negative 2 times 3 is negative 6. Negative 6 plus 2 gives us negative 4. 0 greater than negative 4 is true. In the second inequality, substituting 3 in place of x and 0 in place of y gives us 0 greater than negative 3 minus 1. This implies 0 greater than negative 3 minus 1 gives us negative 4. 0 greater than negative 4 is true. Region 4 satisfies both inequalities. This is an attestation that all order pairs in this region satisfy both inequalities. Thus, we can show this region by shading or drawing lines like this. If we are given with the graph of a relation, we can find the graph of an inverse relation by reflecting the given graph across the line y equal to x. This is because of the fact that when we reflect an order pair a, b across the line y equal to x, we will get an order pair b, a. By observing this graph, we can find the domain and range of inverse relation as well as the original relation. Domain of R inverse, which is always equal to range of the original relation, equal to the shaded region extends to the right and to the left on the x-axis indefinitely. Thus, domain of inverse relation or range of the original relation is a set of all real numbers. Range of inverse relation, which is always equal to domain of the original relation, equal to positive y values and negative y values are points on this graph because the shaded region extends upward and downward without limit. Hence, range of R inverse or domain of a relation is also a set of all real numbers. This relation is not function because if we draw a vertical line on the shaded region, it crosses the graph at more than one point. This concludes part 4. Thank you very much for watching my video. See you on part 5.